Hello everyone. Thank you for attending my presentation. My name is Omar Haija and I am a PhD student in Advanced Information Technology in Castilla-La Mancha University. Today I will be discussing the Hussein search algorithm, its mathematical model and its application in optimizing search operations on inverted indexes. This work is in collaboration with Dr. Arwa Zabian. Motivation slide. Information retrieval systems like search engine must handle millions of unique terms. The dictionary lookup step is crucial and traditionally relies on binary search, which runs in O logarithm of n. As vocabularies scale to millions of entries, even long-time search becomes a bottleneck, especially inside tight loop where queries arrive continuously. Our goal is to design an algorithm that brings the dictionary lookup closer to constant time, while remaining lightweight and easy to integrate. This is the motivation behind HSA. Let me briefly recap the structure of a classic inverted index. We have a dictionary of unique terms sorted, and for each term, a posting list. This structure is used in engines like Hussein and Elasticsearch. The bottleneck we target is the dictionary lookup, not the posting traversal. In a large-scale systems, improving this step leads to a significant speedup. Hussein search algorithm slide. Before describing the model, let me illustrate the classic algorithm. First, assay divide item value with average of average. Second, it organizes them into buckets. We then verify inside a small bucket where is the first and last candidate element and save it. This process makes the lookup almost constant in practice. The example by hand in the paper demonstrates how prediction buckets indexing directly can narrow the search region. HSA citation. Prior work introduced the concept qualitatively. Our contribution is the mathematical model and large-scale evaluation. The mathematical model slide. Formally, we start with the vocabulary T from T1 to Tn. Each term is hashed using FNV1A 32-bit. The hash values are sorted into an array A. A mapping O of I maintains the link from hashed order back to the original dictionary. This model allows us to build the bucket structure in a deterministic and analyzable way. Purpose Sync phase slide. The purpose sync consists of 4 steps: hashing all terms using FNV1A, sorting the hashed values, which is the most expensive step because it is O of n times logarithm n. Third, computing the average of average, which determines bucket distribution. 4. Building the bucket array, both array B and array C, where each bucket contains the terms whose hashed value map to that region. This phase is done once. Search phase slide. Querying works in 4 simple operations. First, it computes the hash of the incoming term. Second, compute its predicted bucket index using the normalization equation. 3. It scans the bucket, which typically contains between 1 and 10 values. Fourth, verifying the term and retrieve the posting if found. Because buckets stay small and stable, lookup time becomes almost constant. To integrate HSA into inverted index, we simply replace the dictionary binary search with HSA lookup. This allows constant time bucket probing, significant speed improvements, and compatibility with both existing and non-existing query terms. Thus, HSA can serve as a drop-in replacement for the dictionary lookup stage. Experimental setup slide. Our experiments were designed to test HSA at different scales. Dictionaries from 5,000 to 2 million terms, query size from 3,000 to 1 million queries, test run on a MacBook Air i5 with Python 3.11.9. We compared binary search versus HSA for existing terms and non-existing terms. The datasets were randomly generated, ensuring uniform distribution. Results 5,000 terms slide. With small dictionaries, existing terms, binary search takes 1 second, mostly 1 second. HSA takes 0.2 seconds. The speed up is 80%. For non-existing terms, binary takes 0.2 seconds, while HSA takes 0.114 seconds, and the speed up is 29%. At this scale, HSA benefits strongly from its constant time structure. Results 500,000 terms slide. At medium scale, the existing terms as following. Binary search took 32 seconds, while HSA took 24 seconds. For non-existing terms, binary search makes 27 seconds, where HSA makes 25, which is faster, 6% faster than binary search. Here, bucket stability remains good, but hashing collisions slightly increase, scanning costs still giving meaningful improvements. The results of 2 million terms slide. At very large scale, existing terms binary search took 106 seconds, while HSA took 73 seconds, which is 30% speed up. In non-existing terms, binary search took 228 seconds, while HSA took 101 seconds, which is 56% speed up. We can see that non-existing queries benefit the most because HSA avoid deep binary search stacks entirely. The analysis of experiment slide. Across all experiments, speed up range from 6% up to 80% speed up. Bucket sizes remain stable, keeping search nearly constant time. The main limitation observed is collision rate in 32-bit hashing at large scale. We conclude that switching to a 64-bit hashing will further reduce bucket expansion. Overall, the mathematical model predicts performance accurately. The contributions slide. Our work offers 4K contributions. First, the first complete mathematical model of the Hussein search algorithm. 2. A bucket-based lookup framework that behaves like O of 1 in practice. Third, large-scale validations on up to 2 million terms. Fourth, demonstration of significant speed gains over binary search, particularly for large vocabularies. Conclusion and the future work slide. Let me conclude with the main message. SHA improves the dictionary lookup performance and scales efficiently to millions of terms. As for future work, we plan to explore dynamic indexing, parallelization of HSA, using 64-bit hashing, and integrating HSA into full information retrieval engines such as Hussein. Thank you for your attention. Question slides. Thank you for your time and attention. You can add me in LinkedIn or send me email using my QR code. I'm happy now to answer any questions.